Hello, everyone. Thank you for joining us in Kemet's Design It Day. We're very glad that you have managed to join us here today. My name is David Adib, and I am Kemet's Senior Technical Marketing Engineer here in Florida. And the topic of this session is load transients. And our speaker today on this topic is Sam Accardo. And Sam is one of Kemet's field application engineers. This session is scheduled for a total of 30 minutes. During the session, if you have questions, you can send us your questions through the Q&A function in your Zoom window. Usually it's located at the bottom of your window. Please do not use the chat function. We will try to get to as many questions as time permits at the end of our session. With that said, I will turn it over to Sam, who will introduce himself and dive straight into it. Sam, please go ahead. Thank you.
Thank you, David. As David mentioned, my name is Sam Accardo, and I'm an FAE at Kemet. I'm currently based in our Northeastern office, which covers the Northeastern US and Canada. A little bit about myself. I've been with Kemet for around 2.5 years, and I joined directly out of college. I have a Bachelor of Science in Electrical Engineering and a Bachelor of Arts in Mass Communication from Louisiana State University. So as the title of this presentation states, today we're going to be talking about load transients, but I think it's important for everyone to really understand what a load transient is. So what I would like everyone to do is close their eyes right now and picture themselves either 20 or 30 years in the future. And imagine walking out to your car and getting in your car, closing the door, and the first thing that you hear is the car asking you, where would you like to go? And so you give it a destination, and without further ado, the car starts driving down the road. So the car is not just driving down the road at this point in time. Your vehicle is most likely going to be fully autonomous. And it's going to be doing a lot of things, actually. So it's going to be looking at the lines in the streets. It's going to be looking for the red lights and the stop signs. It's going to be paying attention to other cars around. It's going to be watching out for rain. It's going to be watching out for a kid that might have just thrown his Frisbee into the road. And it might even be watching out for people that are about to run a red light or stop sign. And that's just on the outside of the car. On the inside of the car, it's also got a lot of things going on, such as the infotainment center that is probably playing videos or music. And what I'm saying is there's so much going on inside of this car. So after a little while of traveling, you finally end up at your final destination. And that's when the car pulls into its parking spot and then puts itself in park and turns off all of those systems all at once. And all of that built up energy, that is a transient. It is a short-lived burst of energy that is caused by a sudden change of state. So that is what we're going to be talking about today. So DC to DC converters are a type of switching regulator whose job is to take one DC voltage and turn it into another DC voltage. So there's an input voltage, and if you boost the voltage, that is a boost converter. And if you decrease the voltage or drop down the voltage, that is called a buck converter. And so the regulator's job is to take an input voltage that may have some type of variation and maintain a stable output voltage. But the thing here is when the load current changes, the voltage changes. And that's what you are seeing right here. So the key thing I want everyone to understand, and the reason that we're actually discussing this topic today, is that even though the regulator's job or the regulator is supposed to maintain a steady output voltage, it does not actually do that because of the change in the load. And it actually takes time to adjust. So one thing that you need to understand about the regulator is that the better the regulator is, the less time it's going to take to settle that change in voltage and get back to steady. And then the less it's going to overshoot and undershoot that voltage. And so that is called the transient response. So today's agenda, we're basically going to be talking about how to calculate the inductor and how to calculate the capacitor values that are needed for this system. So we're going to start with the inductor. And as you can see here, we do have a formula for this, but I want to point out that if you look in the controller's data sheet, typically the controller is going to list a value or a range of values of inductances that you should be using in their system. So if that is the case, you could skip this step and go straight to the capacitor. But for the sake of this presentation, we're going to talk to you about how to calculate that inductor value. So looking at this formula, we have the inductance is equal to the desired output voltage multiplied by the input voltage subtracted from the, or minus the output voltage. All of that over, and I'm going to start with this minimum switching frequency. The switching frequency can be pulled from that controller's data sheet as well, multiplied by the input, and then multiplied by this estimated inductor ripple current. And what you'll notice here is that we've added a formula for that. And so the best way to calculate the inductor's ripple current is by taking anywhere from 20 to 40% and multiplying that by I out max, which is the maximum output current that is necessary for your application. So taking some values, there's a few values that you could pull from the data sheet, as I mentioned, FS, which is the switching frequency. We took 12 volts as VN because that's a typical buck converter's input voltage. And then we came out with V out as 1.2 volts. And that's going to depend on what your load is and what you're working with. And then we're doing our calculations down here for the ripple current. So 20% of, in this case, we chose 300 amps as that full output load current. So 20% of that is 60 amps and 40% of that is 120 amps. So taking all of these values and then inputting it into the formula from the previous slide, you get two separate equations, one for 120 amps and one for 60 amps. And what you see here is that we have two inductances, and there's two important considerations here. The first is that the lower inductance value is going to have a smaller size solution. The second is that the higher inductance value is going to have a higher max output current, and that is going to be because of this lower ripple. And then the third consideration here is and probably going to be the more important of the three, is that the inductor must always have a higher operating current than the max operating current of the system, which is 300 amps. So that is very, very important. So which of these two values are we going to use for our solution? And I'm going to go ahead and tell you now we're going to use 15 nanohenries. And the reason being is because if we look at the capacitor calculation formula, the inductor is being considered in this, this formula. And if it's 15 nanohenries, we're going to have a smaller minimum capacitance requirement as opposed to if we used a 30 here. So we're going to go with 15 to make sure that we're using the smallest possible value. Now, looking at COUT Min, this is the minimum output capacitance, or the capacitor itself, is typically selected based off of the capacitor's ripple current rating, as well as the load transient requirements. So the capacitance output minimum, that is going to be the minimum required output capacitance, and it's going to be used to absorb the inductor's overall energy that's coming from the inductor, as well as to limit the overshoot and undershoots that we mentioned a few slides ago. And that's going to be whenever the part's transitioning from, or whenever the converter's transitioning from high load to no load, or from no load to high load. And so those are a few things to consider about COUT minimum. Now, looking at the formula, what we have here is we have the inductance value that we calculated multiplied by I squared, which is going to be the transient current change from high load to minimum load. What I want to point out here is that this can be the 300 amps that we were just looking at on the previous slide. However, we are going to consider that the minimum load here is going to be 10 amps. So 300 minus 10 amps is going to be 290 amps. And then all of that is going to be divided by a few different things. So it's going to be divided by 2 times, and I'm going to skip this for a second, multiplied by the duty cycle. The duty cycle is going to be V out divided by V in, where V in is going to be the 12 volts, the total 12 volts from the previous slide, and then minus V out. And then all of that multiplied by V out UV. So V out UV is the output voltage drop, which is the sum of the voltage drop while the inductor is ramping up to support the full load, and the voltage drop between before the next pulse can occur. So one thing I want to point out here is that this value, this V out max or V out UV, it's typically going to be placed in the controller's data sheet as well. You're going to usually be able to find an actual value such as 50 millivolts. However, sometimes they list it as a percentage, such as 1%. So if it is listed as a percentage, you would just multiply that percentage times V out, and you would get that value that you're looking for. So now we're going to talk about putting these values into the actual formula and coming out with the actual capacitance that you need. So we took 15 nanohenries and we took the 290 amps, and then we took the 50 millivolts. This is pulled directly from the data sheet. We took the duty cycle, which was V out divided by Vn. We took Vn and then V out, placed it into this formula, and we come out with 10.5 millifarads. And you know, with that, you would think you were done with this equation and that you need roughly around 23 capacitors, because essentially to get 23 capacitors, you would do this number divided by, this number divided by 470, and you get roughly around 23 capacitors. But that is not actually the case, because we did not consider one important aspect here, and that is going to be the ESR of the capacitor, because the capacitors have something called the parasitic elements, and that's going to be ESR, equivalent series resistance, as well as a parasitic inductance. And those things, or at least the ESR in this case, need to be considered. So we're going to use a capacitor that is rated 470 microfarads, 2.5 volts, and 5 milliohms. And this typical type of capacitor would be something like a tantalum polymer or an aluminum polymer. So going back to the equation that we had before, you could see here that the only thing that's really changed here is we're now subtracting from V out UV the voltage drop due to the ESR. And so what we would end up doing is, and we're going to have to come up with the voltage drop and what that actually is. So what we would do is we'd come up with this equation. The voltage drop is actually due to the ESR is going to be 2 times the ESR divided by the number of capacitors that you've placed in parallel divided by that current that we calculated earlier. And so I want to make it clear here that we are considering the decrease in capacitance due to placing these capacitors in parallel. And if you don't believe me, here's the math. If we take the ESR of one capacitor, it's 5 milliohms, and we're placing one of them on the board, then it's going to be 5 divided by 1, which the ESR is 1. On the other hand, if we're taking the same 5 milliohm capacitor and then we take 5 of them and put them in parallel, then it's going to be 5 divided by 5, which is 1, which agrees with the capacitance rule on what happens when you place them in parallel. But as you can see here, we have another number that we do not know what this is, and this is the number of capacitors. So how do we calculate that? I kind of mentioned it on a previous slide. It's the output capacitance minimum divided by the effective capacitance, which is 470. So replacing these values, what we see is we have a few formulas with only 3 missing values. So solving for these 3 values, what we end up doing is we take the number of capacitors and we put that inside of this formula. And so we have the voltage drop due to the ESR is equal to 2 times 5 milliohms over COUT minimum divided by 470 microfarads, all that multiplied by 290 amps. And then we take this formula and place it into here. And essentially what you're left with is a COUT minimum on the left and a COUT minimum on the right. Solving for COUT minimum, you get the value 37.783 millifarads of capacitance needed, which is equal to 81 capacitors. So taking into consideration the ESR, we need 81 capacitors for this bank. Not taking it into consideration, you would only need 23. So why is not taking it into consideration the case, or not the best case here? Because whenever you have the full load transient, your smaller bank, which is roughly 1/4 of the size, is not going to be able to handle that full transient. And so you need to go back and consider the ESR. So now we want to give you another idea of ESR and how that affects it. So now we're going to look at roughly the same type of capacitor, but this time using only 3 milliohms of ESR. So this type of capacitor is typically going to be an aluminum polymer type capacitor. One thing I want to mention before I head on to the next step is that the value that you see in our data sheets is typically worst case scenario ESR. So if it says 3 milliohms, we would never ship the part with 3 milliohms of ESR. So essentially, you're actually going to need less capacitors than we're calculating here. And that's why it's always a good thing for you to take measurements of your devices before you design them in. So looking at the same exact equation, we didn't change anything from the last stop. We're still considering voltage drop due to the ESR. We now have the same formulas that we need to solve for the same three unknowns, but this time we're going to be using 3 milliohms of ESR instead. So inserting the COUT minimum into the voltage drop, and then inserting that into the COUT minimum formula, we get a new value, which is 26.879 millifarads of ESR that's needed, which is equivalent to 58 capacitors. So comparing this, we have taking into the lower ESR into consideration, we need less capacitors than considering the higher ESR capacitor. And then we need actually a little bit more than we would have considered if we didn't consider ESR. So essentially, you know, it's very important for you to consider the ESR when you're calculating the capacitance requirement to support that load transient, whether it's coming in or going out of the capacitor. So with that, I'd like to go ahead and open it up because that is the end of the load transient and see what type of questions we have.
All right. Thank you, Sam, for your presentation. That was pretty good.
Thank you.
I liked it. I do not see that we have received questions as of yet. I'll just give it a minute or two if anyone has any questions. Okay, they actually started coming in already. All right, so the first question says ESR ratings are maximum.
Yeah, that is actually correct. So the values that we put in our data sheet, that ESR level, is going to be the maximum or worst case condition of ESR. So for instance, if it's a aluminum polymer and we say that its ESR is going to be 5 milliohms, the worst case scenario that you are going to get when we ship those parts is 5 milliohms. Typically, the values are going to be less than that. You could think somewhere between 2-3 milliohms maybe, but it's always a good idea, and it's going to vary by batch as well, but it's a very, very good idea for you to measure the parts yourself so that you know where those parts ESR is going to be. And it's also important to measure it according to the specifications in the data sheet at the same frequency, temperature, whatever we say, that, you know, it's very important to measure it with whatever we've said to measure it as.
Okay. All right. Let's see if we have any other questions that came in. Okay. I do not see any. Okay, here it is. Oh, quite a few actually came in. So the next one is, how do I measure that? Following up, I guess, to your explanation.
Well, I think the best way to probably measure the ESR of a capacitor is to apply a voltage and then measure the current. Well, yeah, I think, well, that's going to be the leakage current. So there's probably some type of machine that they use to measure them, but I would suggest, and I could, if you email me after this presentation, my email should be on the right-hand side of the screen. I'll provide you with more information, but on how our team actually measures it and what they use to measure it. But what I would definitely suggest is to make sure that you are following the guidelines that are specified in the data sheet, because in the data sheet, it's going to say that that part was measured at a specific frequency, and you need to be measuring it at that frequency, or else you're going to get a value that is completely off than what it should be.
Okay, gotcha. Okay. I guess the next question is also a follow-up question of that. For a multi-phase converter, the same considerations apply, or do the same considerations apply?
Is that something like a buck boost? And if so, yeah, it's going to be the same types of considerations, but there's going to be different types of formulas. I know in our presentation, we focused on the buck converter, but the boost converter, the buck boost, all of these different types of converters are going to have different formulations on how you're going to calculate these, but the same types of considerations need to be considered here, yes.
Okay. And will the ESR change over the life of the capacitor?
Most likely it will, depending on the type of, well, I would say probably all of them, yes, but more so for the type of capacitors that you're looking at. And if you're using, and I don't know if you would be using one of these in this type of application, but if you're using an electrolytic capacitor, the ESR is going to change a lot more than probably a tantalum or ceramic will over its life. But yes, the ESR is going to change over its lifetime. Absolutely.
Okay.
And I see that there was one other question that we might have missed, and it was submitted by Anonymous, if you'd like to read that.
Yes, that's going to be my next question. Are there some practical applications on which are used so big amount of capacitors, or it was just as an example?
So I think this one here is probably an example, but I think a lot of the newer systems that are being designed probably, and this is something I could talk to our director of application engineering on, but I think a lot of the newer systems are going to be using much more higher powers, and they're probably going to be using or going to have higher loads than the older type systems. And if that is the case, then they were probably going to have or we're going to require higher banks of capacitance. I know a lot of the values that we've used in this particular problem were based off of real controllers and real ICs. And so I think the bank that we're looking at here could be very much possible, but that is something I'd like to discuss as well with my my manager. But feel free to email me, and I will reach out to him and get you a proper answer for that.
Okay. Let's see if we have any more questions, or if there are any questions that I have not asked so far. Okay, I think I've pretty much covered it all. All right, so I guess this should conclude our session for today. So thank you once again, Sam, for this presentation, and thank you to all of our audience for joining us today. And until next time, I wish you all a great day. See you next time, and goodbye.
Thank you, everyone, and thank you, David, for hosting.
Thank you, Sam. Bye-bye now.
Bye, everyone.